Hi, this is Mike Kent for ITSE 1329, Programming, Logic, and Design. I'm coming to you from my home office, or as I prefer to call it, the Nerd National Communication Center. This is the lecture for Chapter 1. It's not a very long chapter, so we're only spending 1 week on it. By now you should have watched the orientation video, you should have created your MindTap account, and you should have gone through all the different materials on Blackboard so you could get a 100 on your orientation quiz. So now we're going to do some real stuff. We're jumping into Chapter 1. As always, email me, text me, call me if you have questions. All right, let's jump into Chapter 1 of Programming, Logic, and Design, ITSE 1329. It's a fairly small chapter, 37 slides, couple introductory, couple are summary at the end. Let's go. In this chapter, here's our objectives. What's a computer? Simple program logic, pseudocoding, flowcharting, programming models. We're going to see some stuff. So what are parts of a computer? Computer system is everything, right? Hardware is the parts of the computer. The software is going to be broken into the programs we use and the operating system. So application software is why we buy the computer. The system software is what runs the computer. Now, what's a computer do? It does input, takes in data, numbers, mouse movements, keyboards, camera, input, processes it, calculates, and then output. So input, process, output. Now, if we want to write a program for a computer, we're going to be writing program source code, and those are going to be in languages such as Visual Basic, C#, C++, or Java, or Python. We're going to be doing primarily C++ in this class, and as we write that C++, we're going to be obeying a set of rules, or the syntax, the grammar of the programming language, which is how we have to write the sentences in the language. We have to do it exactly, otherwise it will not compile. Other parts of a computer is we have the computer memory, which is random access memory, which requires electricity to hold its values. It's volatile. It's called volatile memory. If it loses power, it goes dead. And then we have permanent storage, like your hard drive or your SSD. That is non-volatile memory. SD card, USB memory stick, that's non-volatile. Now, when we've written our source code, we're going to run it through a compiler or an interpreter. It's going to take our source code and turn it into a machine executable, a binary file that the CPU of the computer can run. So this is called object code. It cannot create that binary language if you have syntax errors. So it will give you a list of errors that you need to correct. So once you've got it compiled, then you can execute the program, or you can run it, and it's going to do hopefully what you designed it to do. Now, if it doesn't compile, you've got syntax errors. But you may have bugs in your code, so you have logic errors. That means it's all written correctly. It doesn't have any syntax error, but you're telling it to do the wrong things. So a logic error is a flaw in the code you've written. You're telling the computer to do the wrong thing, and it's making bad things happen. Okay? Now, as we're running our programs, we need to get values from the user, get values from different input sources, and output them. They need to be stored in random access memory, and we give that memory location that holds that value, we call it a variable. A variable is a named memory location whose value can vary. That's why it's called a variable. So we're going to create variables to hold values and do calculations, get a calculation stored as a result in a different variable, and then we're going to output it to the screen so the user can see it. You need to know the program development life cycle. Uh, this is very much like you'll see this in almost every programming book. So before we can write the program, we have to understand the problem. Then we need to plan the logic. We need to make sure we understand the problem so we can plan the logic correctly. Then we're going to code. We're going to write the source code. Then we're going to compile it to translate it into machine language. Then we got to test it, make sure it's working correctly, put it through a test regiment, and then we're going to put the program into production. And as it's in production, we're going to have to maintain the program. We might find a bug later on. We may have to modify the program to add new functionality. Say it's a tax program, you've got to change it because of the tax law, or you need new features. So maintenance and modification takes up the bulk of the expenses in writing software. But this is the program development lifecycle. And once you've gone all the way around, it leads to right back into the life cycle again. Once you've maintained the program, now you've got to understand the new problem because you have to modify the program, which leads to planning the logic, etc., etc., etc. Understanding the problem. This is really the difficult part. The old programmer's joke is, I'll go find out what the user wants. You start writing code. No, you need the input from the user. You're writing the program for the user, so you need to have the patience to find out what the user wants and document that so that you are solving the correct problem. One of the things they had to do at NASA during the shuttle era is they had to take the ground support software that talked to the shuttle, that processed all the telemetry coming down, let the ground controller send commands up to the shuttle. It was running on an IBM mainframe and they needed to move it to more modern hardware. So what they had to do first was exactly document how the existing software worked in minute detail, so that they could write a brand new system that worked exactly like the old system, would talk to the space shuttle the exact same way that the current system did. And they needed to move it to new systems because the hardware was getting so old you couldn't get it, you couldn't maintain it. There was no room to improve it because the processor wasn't going to be any faster. It was like trying to run the new version of iOS on a really old phone. It's not going to work. So they had to meticulously document how the existing software worked. They had to understand how it worked before they could write the new program. Planning the logic, that is usually done if you have to plan out your code. You do it in pseudocode, which is kind of like a pigeon programming language. You're just kind of writing it out. It's not a real programming language. It's also done in flowcharting. So the book is going to show you both ways as we go through things. And then once you're writing that logic and planning the logic, you got to think through your head, is it actually working? And we call that a desk check. That's where you're looking at your logic and you're running the program in your mind, as opposed to trying to run it on the computer, because you can't run it on the computer because pseudocode is not C++ code and will not compile. A flowchart is not object code that can be compiled. This is a tool. Flowcharting and pseudocoding is a tool to help you design and think your way through a problem, and then you look through the code and see if it's running correctly. Being able to look at the code and understand what it's doing is paramount to being a good programmer. So once you've designed it, once you have planned the logic, banging out the code is easier than the planning step. To me, one of the most interesting parts when I was a professional programmer was planning a system, how it was going to work, how the data was going to move around, the things it was going to do, and understanding how all that was very, very creative. Once I did that, it was just a matter of writing the code. It was like, you bought your favorite piece of furniture from IKEA, and now you got to put it together. That's not as exciting as designing the piece of furniture. So coding the program is generally easier. And if it's a simple problem, you can definitely combine the logic planning and the coding steps. If it's a complex problem, you need to design it before you code it. So now we've written our source code and we need to turn it into an executable program that the CPU, the central processing unit of the computer, can run. So that's a translator program. It can either compile it, which is a one-time conversion to machine code, or an interpreter that takes each line of code you've written, turns it into machine code, has the CPU run it, and then it compiles the next line of code and runs it. It does that repeatedly. So interpreters are much slower, but they're more flexible. Almost everything we see nowadays is a compiler. Visual Studio is a compiler. There are tons of C++ compilers online and free ones. It's compiling the high-level programming language, C++, into the low-level machine language binary. If you make a typo, that's a syntax error. That's where you break one of the language's grammar rules, like in the orientation video, you saw where I left a semicolon off. And C++ don't like that. So then you have to correct your syntax errors and recompile the program and see if it runs. And rinse and repeat until you get the whole thing working. So here's the steps you're looking at. We're writing the program, we compile the program, we get our errors, we fix it. We're in this stage until we get it running. Then we have an executable program that inputs some data, outputs some data, and hopefully works correctly. A logic error is the program compiles and runs, it just doesn't run correctly. And that's where we need to test our code, and we have to debug our code. We have to get the bugs out of our code. That's the process of finding and correcting program errors. So you need to test your programs with many different sets of data to have an assurance that it is working correctly. Once we've gone through coding, compiling, and testing, we're ready to put our program into production. So now it's making us some money. It's adding functionality to the company. People are happy. They're playing their games or whatever. One thing you can have happen is you need to move a program from one platform to another. I've written the program for Windows. I want to move it to the Macintosh. I've written the ground processing software for the Space Shuttle system on an IBM mainframe. I need to move it to Unix workstations. That's a conversion, okay? Maintenance. As you run a complex program, you will find bugs and you will have to fix those bugs, or you will have to make changes to the program to keep it relevant and up to date. And that just throws you back into the program development life cycle. You going back to the beginning and going around that circle again. Pseudocode. This is a way we think through our logic. We can do pseudocoding or flowcharting to think through the logic of our program, the steps of our program, to make sure we've got it right. It's a good way to visualize it. So pseudocode will be something with a start and a stop. So it's not an actual programming language, but here we're saying input from the keyboard into a variable called myNumber. myNumber times, we use asterisk for multiply, times 2. Double this number, put the answer into my answer, and then output my answer. So a very simple program that has been pseudocoded. So you're going to mark your pseudocode with a start and an end, the same thing with a flowchart. And if you're breaking your program into modules, the modules are going to have a module name you put at the beginning of them. And then they usually end with a return statement that makes it go back to where it was called from. So each programming statement is doing one thing. It's doing an input, it's doing a calculation, it's doing some processing, or it's doing output. Input, process, output. Pseudocode, usually the stuff that is inside of a module is indented a few spaces for readability. Each program statement should appear on a single line if you can do it. If you have to word wrap it, you want the subsequent lines to be indented. Program statements begin with lowercase letters. That's not an absolute. And you're not using punctuation. You're not putting semicolons at the end of each line like C++ or different programming languages expect. Flowcharting, we use different symbols to stand for stuff. Like if we're inputting something, we use a trapezoid with, the leaning sides. This is for input. I'm going to input my number. I write that inside of it. If I'm going to do some processing, I have a square. I have a rectangle saying I'm doing some processing. And if I'm outputting, I use the same symbol for input output. It's that trapezoid, that leaning rectangle for input and output. Terminal symbols, you're going to have a start symbol at the beginning of your flowchart and a stop symbol at the end of your flowchart. And you're going to use lines with arrows between these different objects to show the flow of logic. What's the next step? So here is a flowchart that's doing the same thing as a pseudocode. These two are equivalent. Start, input my number, multiply my number by 2, put the answer into my answer, output my answer. This is the same thing. I personally like pseudocoding better than flowcharts, but this is a little bit more visual. Sometimes it's a little easier to read and understand this, but if I'm thinking through a problem, I'm pseudocoding. That's just me. Repeating instructions. The problem with this figure right here is it runs one time. If we want to do 1,000 numbers, we have to run the program 1,000 times. It's not feasible to add that same set of code 10,000 times to the program. So what we want to do is create a loop known as repetition to do a series of steps multiple times to keep doing them. But you've got to be careful, because if you don't do it right, you'll have an endless loop and it will run forever and the program will not respond and the computer will get locked up. So we do not want to do it this way. And when you see this in the book, it says don't do it. They're giving you a bad example, because here they've done it 3 times and they need to do it 9,997 more times. We don't want to do it that way. We want to write a loop. Now, if we write a loop like this, which says do this step, do this step, do this step, go back around and do it again, problem is this just doesn't do it 10,000 times. It does it forever until you kill the program. So we don't want to do it this way. So we need to add a decision to our program to see if we want to continue, where you're testing a value. If the user inputs -1, we exit the program. Or if the user just presses enter with no value, it exits the program. So we might have a dummy value, a sentinel value that's called, to say when a certain value is inputted, that means the end of it. If you're reading from a file, you just simply read until the end of file, EOF, becomes true. So now, in structured programming, we don't want to do it this way. We want one entry point and one exit point. We don't want to just short circuit out of the loop. What we want to do is have this, you want to have your entry and exit point of loop at the top of the loop or the bottom of the loop. They'll talk about that more in a later chapter. So you don't want to do it this way because it's not structured, and you're going to learn about structured programming in chapter 3. Now, when we're writing our program, it could be as simple as opening up a text editor, opening up Notepad, and writing the code. But Notepad doesn't understand C++. If you're using an integrated development environment, an IDE, as you write the code, it will help format it, it will color code it, it will make it easier for you to read the code and understand the code. We can write 2 types of programs. We can write command line programs, which is what we're going to be doing this semester for C++. We're going to be inputting from the keyboard and just outputting to a command line type window. Or it can be a graphical user interface, a GUI. So if we're saying, like, this is C#, and C#, if we say write, it's writing it to a command prompt. And if we're doing a write line, that's writing out a message. Here we're doing an input, so we're doing a read line. The resolution of this picture is not very good, but this is a command line type interface, okay? Versus here's an IDE where it's color coding everything. The keywords that are part of the programming language, reserved words, are in blue. The name of my function is main. The name of my variables are in black. The strings I'm outputting are in red. So you can see it's color coded to make it a lot easier to understand. The green lines indicate this code has been saved. All those changes have been saved. So an IDE for like Visual Studio is very nice. Now, when you run the program, we're in this command line interface. Please enter a number, 13. 13 doubled is 26. Press any key to continue. So that's not a graphical user interface versus here we're using a text box for input and a label for output, and we'd have a command button for the user to click to trigger the calculation. So the first digital computers were developed in the 1940s, actually towards the end of World War II. They were actually made with vacuum tubes, very large, used huge amounts of power, were immensely pathetically slow compared to anything we have today. And we've just come so far. The newer programming languages we're using today are closer to natural programming languages, more like speaking a natural language. They're self-contained, they're easier to understand. So we are going to be looking at object-oriented programs versus procedural programs, procedural programming versus object-oriented programming. I cannot even begin to get into that in Chapter 1. And that brings us to the summary slide, which means we have reached the end of the Chapter 1 lecture. So go through your material, get your Chapter 1 quiz done, do your coding exercises on MindTap and your Chapter 1 reading quiz on MindTap, and that will be it for week number 2. Take care.